Okay, so we concluded that our experiments or our imaginary experiments require that particles be described by objects like this, right, waves. And so now let's start to explore the kinds of results that we get by imposing this kind of an object as a description of a particle. And let's simplify things by imagining that we have a one-dimensional universe. Right? So here's a one-dimensional universe, and we'll call it the x direction. And so we have an object that obeys the rules of quantum physics. And so we're going to describe it by an object like this. It's just free to move anywhere along the x direction, from minus infinity to the left there to plus infinity to the right. And so this k dot r, right, so k dot r, which is in xyz coordinates, this would be kx times x plus ky times y plus kz times z, because r is, right, so the k vector is kx, ky, kz. Those are the components of k, and the components of r are x, y, and z. And so the dot product gives us this number. Okay, but this part disappears because the object doesn't live in the y and z directions. So here is the object that purports to describe this particle. We get e to the I, let's just leave it as k times x minus omega t. And we could replace, p equals h bar k. Now this is a px. So we could say, we could write this as a e to the I times p over h bar x minus, right, we're writing things in terms of their particle properties. And so we could say that E t over h bar is this part. But otherwise, it's the same kind of object. It's this wave that is traveling to the right, and we wanted to describe this one-dimensional particle. Well, we know that from the experiments and from the intensity on the screen that we saw was described mathematically. So intensity I was the psi modulus squared, right? We concluded that. And so this is also the probability. In this case, it's just A star times A, because A could be a complex number. So when we do psi star psi, right, so this comes from doing psi star psi, but psi star is A star e to the minus I times p over h bar x minus e over h bar t. And when we do that times psi, which is just a e to the I, right, so that looks like that. And of course, this ends up being 1. This times this ends up, sorry, this part times this part ends up being 1, and we just have A star A. And so the intensity, or the probability density, is A star A. And so we have to integrate this quantity, right? If we integrate this quantity over the entire possible space where the object can live, we expect this quantity to give us 1, because it must be 100% that we find it in the universe in which it can live. So let's see if this is possible. So we know that this becomes A star A. That's just some number, so we can pull that out, A star A. And so we end up with an integral in dx. And that gives us A star A. That gives us x from minus infinity to plus infinity, which of course is just A star A times infinity minus a minus infinity, which is plus infinity. So it's twice infinity, which is infinity. And so that can only be equal to 1. So can this equal 1? And the answer is only if A star A, or only if A goes to 0. Right, so, but that means that A star A, the probability density, or the probability of finding the particle at one location, is essentially 0. So notice, by the way, that the probability density is a constant. Everywhere it's the same. And so is it possible to describe a physical particle that is as likely to be at minus infinity as it is at positive infinity? And so the answer is no. Basically, we can't do this because it says that the particle has 0 wave function. It basically doesn't exist. And the reason for this is that it cannot be localized. Okay, so this is really the beginning of understanding the uncertainty principle, right? So if we think about the range, right, the range in the x values, right, the range in the x values that are possible here goes to infinity. Right? If we can expect to find the particle anywhere between minus infinity and plus infinity, then the range of possible values of x that we could obtain is going to infinity. But now let's look at the object, which is right here, that describes the particle, and see what its momentum is. There's some value of p that's fixed. So the range in the value of the momentum is 0. Okay, so we've made the momentum range. There's one value of momentum. That means the range in momentum goes to 0, while the range in possible values of x goes to infinity. And so basically we're concluding that it's not possible to describe a localized object using waves if you fix the momentum to one value only. We're going to have a non-zero range in momentum in order to get a non-infinite range in position. And so it's also the case that this term, the uncertainty principle, is a little bit tricky, right? So we're going to get delta x times delta p is going to be greater than or equal to some number. And we'll get to that in a little bit. And we can see this is the first example of that. When the delta x goes to infinity, then the delta p goes to 0. But that's not a localized particle.